Alrighty, welcome back to operating systems. So today, get to figure out how your files are actually stored on the devices, and we'll actually figure out what the hell a file descriptor is and all the fun that comes with that. Hopefully it will explain a few things. So, a bit about file systems, how they're organized, probably review or you've figured this out. So on POSIX, their file systems has like a root directory, and then there's actually a specification that says what other directories should exist. And the specification is called FHS. Very, very creatively named. It's just short for File System Hierarchy Standard. Great fun name. And that defines what directories should exist. So at the top, there's a root directory, and it defines what directories should exist in that root directory. So there'd be like a folder, or sorry, a directory called bin that has all of the binary executables like ls, things like that. Dev, which would have files representing actual physical hardware that the kernel exposes to you. etc, which is supposed to be configuration files. A home directory that should have a directory for each individual user on that machine so they can store their own files. So for example, I might have my own directory called John, and I might have a file in it called todo.txt. If you have Mac OS, they're slightly different, but same idea. Instead of home, it's just /users. And then I might have a directory called mnt, short for mount, and that is a location that has that, like, if you plug in a USB drive or something, all the files on the USB drive will appear in a folder, perhaps called USB, or it'll be named something depending on what you plug in. And that is the basic standard. Now, your processes, when they run, they'll have a working directory, so that's like what current directory are they in. And with that, I can define a path, so a path to another file. In absolute or relative terms, absolute paths start with a slash, and relative paths are relative to the current working directory. So if I was to describe where todo.txt is from the absolute path, it would just be /home, /home/John todo.txt. If it was relative, well, I'm already in that directory, so it would just be like /, that little short form. And then if I want to see what the absolute path is to this USB directory, it would be /mnt/USB, or the relative path, I could use the .. right? .. to go up to home, .. to go to the root, and then mount USB. Everyone's slightly familiar with that, right? So here's all the answers for that. And yes, there are special symbols, so these names actually exist in the directory. So dot is the current directory, and .. is the parent directory. So now, fun history lesson time. So if you type ls, you don't see dot or dot, right? You never see them both. So that's by design, right? They don't want you to, they always exist, so if you just type ls, they hide them for you. So how they implement it, you might think they would just, if the name is dot or the name is .. then don't show it, right? That's 2 if statements. That's a lot of work. What about if you were smarter and only wanted it to get down to 1 if statement? How would you make that a lot shorter? Yeah. Yeah, if it starts with dot, just don't show it. And then, spoiler alert, that bug has now become a feature. So any hidden file on Linux, if it starts with a dot, it is hidden, and that was just a bug because someone implemented it like that. If it starts with a dot, well, that covers dot, and there's no unintended consequences to this, so let us be merry. So that is why all hidden files on Linux start with a dot. It was a complete accident, and that bug has now become a feature. So there's your history lesson as to how hidden files work on Linux. They're not really that hidden, they just start with a dot, and by default they don't show if you type ls. And then the only other special character is this tilde, and that's the user's home directory. It would also be given in this environment variable called home, and relative paths are calculated from the current working directory. That's the environment variable called pwd, or you can use like git cwd, get current working directory, as a C call. Either of those works for that. So that's just like how your file system is organized, and you'll get into how to actually implement this and something akin to this in Lab 6. But before we get into that, let's describe file descriptors a bit more. So through a file descriptor, you can access a file sequentially or randomly. We do not know how to do randomly yet. I will show you it in a second, but first let's understand the difference. So sequential access of the file, that means if I'm reading it, I read it one byte after the other, all in a row. So if I read 4 bytes and then do another system call of 4 bytes, I will get the next 4 bytes. I won't see the same 4 bytes again, and I can do that as long as there's information in the file, as long as read doesn't return 0. And then, so there's like some internal position inside that file so that it just resumes reading from the next byte. If I do write system calls, same idea. They're appended to the position and set to the end afterwards. So if I write, I don't know, the byte, if I write hello and then world in that file, I'll see hello world. They won't overwrite each other or anything like that. If I was to access a file randomly, which I will show you how to do, then we could actually do reads and writes at any individual byte we want. There would have to be like a specific position required for each operation. So I might say, hey, start reading at byte 4 or something like that. So how we do that is, while we have this open system call we know and love, give it a path name, some flags. Flags describe some permissions that you're allowed to actually do on this file through this file descriptor. It can be like reading and writing, write only or write or read only. And there's also this append flag that moves a position to the end of the file initially. So if I start writing, it will actually go to the end of the file and not clobber whatever is there. By default, if you just open a file and write to it, it will write to it from the beginning, so you would overwrite whatever information is there. If you add append, it will start it at the end of the file. Then, if you want to change the position where a file descriptor is going to access from next, you can actually change that through this lseek system call. So it takes a file descriptor and then an offset, which is just the number of bytes, and then this once tells you what those number of bytes is relative to. So once can be one of 3 values. It can be seek set, which is absolute. So if I have seek set, once as seek set and the offset at 8, that means start at byte 8. If I have it at 16, it means start at byte 16. Doesn't matter what the current position is. If I set it to seek cur, that is relative to the current position. So if I want to just skip ahead 4 bytes, I'd set once to cur, and then offset to 4, and that would skip me ahead 4 bytes. And I could also do it relative to the end. So seek end is relative to the end of the file. So I could do once as seek end, offset to -4, so that can be negative, and that would set me back 4 bytes from the end of the file. So I could, if I do a read system call, then I would read the last 4 bytes of that file. So, and then there's the directory run, but we've went over that before. /u did it for lab 1, so who cares about that one? So now I get to tell you what is actually in a file descriptor, because I lied to you a little bit and said like a file descriptor basically points to a file. That is a little bit of a lie. I said you can think of them as pointers. That is correct, but instead, so here in each process control block, this is one for each process, so this would be process 1's process control block. It would basically, have an array of pointers. The index to them is the file descriptor, but they're not really pointing to a file. They are pointing to some entry in the kernel that is keeping track of the current position because, well, if I can manipulate the position, it's got to be saved somewhere. So it keeps track of the current position, the flags, so what access do I have through this file descriptor? So I can write to any file, the kernel can write to any file that it wants, but if you open a file descriptor as read-only, you are not allowed to read or write through that file descriptor, so it has to store that somewhere too. And then the last thing is more what we thought was there. So there is this pointer to a vnode. It's just a virtual node. A virtual node is basically any resource on your machine that you can read and write bytes to. So it could be a real file, it could be a terminal, it could be a socket, it could be a pipe, it could be any one of those. So in the case that it's an actual file, that vnode will point to a file. So I lied to you a little bit. So I said before that file descriptor points to a file. A little more complicated than that. It points to one of these entries in the kernel that one of the fields points to a file, but it also keeps track of the flags and a position. So if I have multiple processes, well, in this one, they're each pointing to its own unique entry in that table. And in this one, well, these two file descriptors in these two different processes might point to the same file, but they would have their own independent position and flags, so one doesn't affect the other one. So everyone okay with that? Because it will get a bit weird with forking. So the file descriptor, like I said before, is an index into that table. Each item points to a system-wide or some table in the kernel. That is called the global open file table. So there's only one of those managed by the kernel. Some people shorten it to GOF, global open file table. So the GOF table holds the information about the seek position, so the current position, flags, and also points to a vnode, which is anything that can read and write, file, socket, pipe, whatever. So that's actually what a file descriptor is pointing to. So remember what happens during a fork. The process control blocks copied during a fork. Specifically for us, you can think of that table, that array, in the process as being a local open file table. So instead of having its own position in anything, the local entries or the entries in the process points to a global entry. That's all they do. So when you fork, that table just blindly gets copied. So they would point to the same global entry. So all the file descriptors point to the same global entry. That means they share position. So that means if you do an else seek in the parent process, it affects the child process because they're both pointing at that same global entry. So things can get a bit weird for us. So if we fork, if we have process one that's pointing, let's assume we have no other file, the standard file descriptors aren't open. Let's say file descriptor 0 is pointing to some global entry here that has its position, flags, and vnode, and it's pointing to some file called A. Well, if we fork, we get a new process control block. It has its own local open file table, and it points to that same global entry. So now if one of them, so now they're sharing that position, sharing the flags, and sharing all the details. So if you read, it will affect the position, or if I else seek or anything like that. So some gotchas, like I said, that current position is shared between both processes. So again, if you seek in one process, all the other processes using that same global open file table are not independent. So it affects all the other processes. So if you really want to screw with your child process, you could just seek to the end of the file or whatever, and then, well, it will never read any data from it. If you open the same file in both processes after forking, the rule here is that whenever you do an open system call, that creates a new entry in the global open file table. So if you want your processes to be independent and read the entire contents of the file, you need to do the open call after the fork. That way they are not sharing a position or anything like that. So if we have a program, assume we have no previously open files, so no file descriptors are open. If we have the following program that just opens to-do.txt as read-only, forks, and then opens b.txt as read-only, well then, how many local open file table entries are there, and how many global open file tables are there? And what is their relationship? So what is pointing to what? So if I start this process, right, they would do an open system call, so that would create a global entry, and in this process it would have its local entry that points to that global. So we have 1 and 1. If we fork, that creates a new process. It has the same amount of entries pointing to the same thing as the parent. So the new process has a single entry pointing to that same global entry. So two processes with one entry each pointing to the same global entry. So one local each, one global, they're both pointing to the same thing. And then if I do open, I don't know which one's going to execute next. If I do open, they'll both create their own global entry and then each point to that. So each process will have two file descriptors open. The first file descriptor before the fork both point to the same entry in the global table. And then for b.txt, there'd be two independent entries, right? So it would look something like this. So 0, that was what we opened before the fork. So when we do an open system call, that's a new position, flags, and pointer to a vnode. That would point to the to2.txt file. And when we fork, the child will have a file descriptor 0, also pointing to that same entry in this global table, which is there's only one of, and it's held in the kernel. Then after that, whenever they independently do their open system call, both of them create a new entry in the global open file table with the position, flags, and vnode, and they're both pointing to b.txt. So everyone okay with that? All right, just to make sure, let's look at some code. So I have two files here. File A that just says this is file A. And then B that says, well, this one is file B. And then I have this code. So it essentially does the same thing that I just showed you. So it opens the file A, forks, opens file B, and then calls this read file function. And this read file function, well, it just calls read, it assumes we can just read the entire thing in one read system call, and then outputs the current process ID, how many bytes it read, and then the string that it read. So if I run this, you don't have to tell me the number of bytes read, but if I run this, what am I going to see in my terminal when I run this? And I'll give you a minute for that. Oh, okay, yeah.
Like the file descriptor 1 is shared, so when one of them reads it, the position gets updated, and when the second one reads it, it's already at the end. So it only points it out once for the first read file.
So for the first read file in both processes, I'll see, say we have, let's say we have process 100. That's the original process that's going along, and it creates file descriptor 1, which is file descriptor, which let's just say it's file descriptor 3, and then we fork. So now we have process 101. It would also have file descriptor 3, but they both should point to that same global entry. I'll just give it a random number. So for file descriptor 1, if they both read file, what should I see? See blue, apparently. So what should I see? So I should see which one executes first. No, pick one, then pick one. 100, okay, so if 100 executes first, it would read, would this buffer have the contents of the file? After the read, yeah, so it should print PID 100, however many bytes it read, and then this is file A or whatever it says. Okay, now if 101 goes, what does 101 print? Nothing? Well, it'll print PID 101, then read 0 bytes and then no string, right? And then what about both processes when they do read file of FD2? That's fine. They should both read what?
This is file B.
This is file B. They should both read the entire file, right? Because they did it after the fork, their positions aren't shared. So if I run this now, exactly what I see. So this is file A, and this was the other process, so I can see only two processes, so I'll just call it 70. Process 70 read nothing. Process 69 was the one that executed first, read the whole file, and then through file descriptor 2, pointing at file B, they both read the whole file because it was after that fork, right? So, also, if let's say file A was huge and I only read little bits of it at a time, between both processes, who's going to read what?
Collate between them?
Yeah, it'll alternate. Between the two processes, I will read every byte of that file, right? But I have no idea which process is going to read what. But between the two of them, they'll read everything in the file. So that is the one gotcha you should be aware of. And that's also why if you type in standard in, only one process gets to read it because it's shared through forking. So as soon as you read input, as soon as one process reads input, it doesn't get replayed for all of them because they're all sharing that position. So that's why if you type in standard in, only one process actually does something with that information. All the other processes do not do anything because they're sharing the position. Only one is going to read that data. So we finally demystified standard in. Yay. So any questions about that? Took us long enough. All right, so now we get to talk about how to actually store files on our hard drive. So some different ways, whoops, what'd I hit? So some different ways we could store files on our hard drive is, well, as we discussed in the last lecture, SSDs just store pages at a time. So if I'm storing a file, I'll just make it easy on myself. I will only consider how many pages I need to store a file. So if I'm thinking about how to store, like actually explain where the contents of a file is, I might do something like contiguous allocation, which is basically like an array. So assume I have a green file. I would say, hey, the green file, maybe it starts like, if we were to describe an array, basically you just tell me where it starts and how big it is. So if I'm doing this to store files, I can use the same idea. I can tell you what block a file starts at and how many blocks large it is if I was describing to you where the contents of a file is. So let's assume we have a green file, a red file, and a blue file. The green file, I'd say, starts at block 0 and is 3 blocks big. The red file, that would be that would start at block, well, 0, 1, 2, 3, 4, 5, 6. Starts at block 6 and it's 6 blocks long. The blue file starts at what, block 10 or something like that, and it's 4 blocks long. Is this a great way to store files? Probably not. Let's think about what happens if I want to make the red file bigger. Then what are my options here? Yeah.
You have to move the blue file, or you can just try to move everything in the red file to the left.
Yeah, I could either move the blue file, get it out of the way, or move the red file and go ahead and move it somewhere else so I can grow it. Probably pretty bad if all these things are like gigabytes. So I have to move, even if I add a single byte to the end of the file, I have to move several gigabytes, depending on how big things are. So this probably isn't the best way to store a file. With virtual memory, does everything have to be contiguous there? No, one block's as good as any other block, right? So we'll probably steal that idea for storing contents of files, But first, let's discuss why this is bad. So this would be a good approach because it's space efficient, like to describe the contents of a file. You don't have to tell me that much information, what block it starts at, how many blocks needs to be stored. Has fast random access, so if you try to access any byte in the file, I can immediately tell you what block it's on. So if you want to access, I don't know, byte 6000, I could immediately tell you it's on block 1 of this file, which is just start plus block 1. Really easy to do, but files cannot grow easily, and we have something called fragmentation, where fragmentation is just another word for wasted space. So for all these, we're going to have some type of internal fragmentation, so that means the contents of a file may not completely fill a block. We're not going to worry about that because we're just going to deal with blocks at a time. But you might imagine if my blocks are 4 kilobytes and I'm storing like a file that's 12 bytes, well, those 4 kilobytes minus the 12 bytes are essentially just wasted space. We're not going to do anything about that. This one also has external fragmentation. That basically means there are some blocks that are useless if you're trying to allocate something. For example, in here, in total, I have, 12 blocks free? But if I tried to make a file that was 10 blocks large, I couldn't do that without moving anything, right? Because even though I have 12 blocks free, I do not have 10 free in a row, so I couldn't create a file with that. So we would call that external fragmentation. All those blocks are pretty much useless, and they're wasted because, well, we can't actually create that new file because there's not enough room here, even though we have enough blocks to do it. They're just not all in a row. So everyone likes linked lists, so maybe I have the idea of like, okay, well, to store the contents of a file, maybe I use a linked list, so I can tell you what block it starts at, and then on each block itself, I'll reserve a little bit of space to store a next pointer on the block itself. So to describe this green file, now it doesn't have to be contiguous. I can just say, okay, well, this file starts at this block, and then just follow the next pointers until the next is null, and that's the end. So that would mean block 0 of the file is block 0 of my device, block 1 of the file is block 6 of the device, block 2 of the file is block 2 of the device, block 3 of the file is block whatever the hell this is of the device, and so on and so forth. So everyone likes linked lists? So this solves that external fragmentation error, or not error, but problem, because one block is as good as any other block. None of them are ever wasted. I just point to it. If I want to make this file bigger, well, I just grab any block and then point my next pointer to it, and I'm done. So this is space efficient, because to describe the contents of a file, I only need to tell you what block it needs to be stored at. Like I said, the blocks need to store the pointer to the next block, so the block would be slightly smaller. But the big thing here is that files can grow and shrink at will. There's no external fragmentation because one block is as good as any other. There's still going to be internal fragmentation, but we're not ever going to worry about that. But this is really, really slow. So remember, SSDs, they access pages at a time. So if I wanted to access, I don't know, the third block of the green file, well, I would have to read in this whole page to read just this next pointer, then read in this whole page to read just this next pointer, then read this whole page just to read this next pointer. So how would I make this a lot faster? So I have to read less pages, yeah.
Have a block at the beginning that tells you where all the other blocks are?
Yeah, it was the same idea. Yeah, just, well, if it's slow to just read a next pointer on an individual block, I'll just reserve a block that just stores all the next pointers. So they're all right beside each other. So this is the first file system that is actually used, and you all have used it whether or not you know it. And it is called FAT, or File Allocation Table. So, any of you have a Windows computer? One person? Two? Okay, I guess we all have Apple machines now. So, if you boot off Windows, this is how your boot partition or your boot drive is formatted. It's formatted as a FAT32, which is file allocation table, and 32 is 32-bit pointers, so that's the size of a pointer. So basically, all that does is reserve some space. So these would just be a block that just contains all of the next pointers. So for every block on the device, it would have a next pointer in a giant array somewhere, and this could actually be stored at the beginning or at the end. It doesn't really matter. For the purposes of this, just assume it's at the end. But it would just be a big array of next pointers. So instead of storing the next pointer on the block itself, this would hopefully all be on the same page, and otherwise it would work exactly the same. So for the green file, it starts at block 0, and to get to any other block, well, I can follow the next pointers in this big array of next pointers. So the index, the values of this array are next pointers, and these are the indexes. So the next pointer for block 0 is block 6. The next pointer for block 6 is block 2. The next pointer for block 2 is block 13, and so on and so forth. So, actually used, but are there some issues here? Yeah?
Isn't it still kind of slow because you have to trace through all the links?
Yeah, it's still kind of slow to go through all the links. Major problem is this gets worse and worse the larger your hard drive is. So the larger your hard drive is, the more blocks and the more next pointers you need to actually store. So it's proportional with the disk size, so it's only really suitable for very, very small things. The nice thing about it is that it's simple. It's quite simple, which is why it's used for boot drives. But the larger it is, the worse it is, but typically boot drives are very, very small. So, has all the same benefits as the linked allocation, but it's actually used. So no external fragmentation, still internal fragmentation. It's faster random access, so assuming that file allocation table, it's just loaded into memory or cache or something like that, it might be pretty fast, but it gets worse and worse as the size of your partition or the size of your disk increases. So if I wanted to increase random access speed for an individual file, how might I do that? So this was slow because if I wanted to access block 3 of a file, I had to follow a whole bunch of next pointers, right? What would be a lot faster than following a whole bunch of next pointers? Yeah?
Can we do something similar to like memory where we have multiple levels of, like you have bigger blocks that themselves contain blocks?
Blocks that contain blocks? Kinda, yeah?
Mine's not kind of like that, but I was just going to say you can do like a hash map and have each index kind of index the blocks.
So what your hash map would be, what would your key be? Like the block of the file to the block on the disk, right? Why would you need a hash map? You do want the pointer. What's wrong with an array? Huh? The search is bad in an array. What do we need to search?
Let's say you want to access the fifth block. Oh, actually it's not.
Yeah, right. So, I don't know who yeah, there's like some weird tendency to always go to a hash table. I don't know why you guys do that. A hash table is just an array. The only difference between a hash table and an array is A hash table will support a very, very sparse index. So if you wanted to create instead of a hash table, you could use an array, but if most of the elements are empty, that's a whole lot of wasted space. You want to compress the size of the array. That's when you use a hash table, right? But for this, if I want to just straight look it up, use an array. I need an entry for block 0 of the file, block 1 of the file, block 2 of the file, block 3, so on and so forth, right? So it's just an array. So that is something called indexed allocation. So basically, what I could do is, and this is where I come into your virtual memory idea. So this is kind of like a single level page table. So I could just say, well, I'll use one of the blocks here to store all of the blocks I use for the file. So basically, I use one of the blocks as my big array. So to describe the file, I would say, okay, well, use this red block. This red block has my array of all of the blocks I point to for this file. So for this is just a big array. We could probably calculate how many indexes are in this array or how many elements are in this array. And then that would mean block 0 of this green file corresponds to block 0 of the disk. Block 1 of this file corresponds to block 3 or block 6 on the disk. Block 2 of this file corresponds to block 3 on the disk, right? Makes sense. All right, with this, for index allocation, we can still grow and shrink files at will. That's great. We have some internal fragmentation. We have really fast random access now. It's an array access, nothing faster than that. But we're going to have a little limitation here. So let's assume, for fun, we have a block size of 8 kilobytes. And let's assume our pointer size is 4 bytes. If I am only using one block to store all of my pointers, 2 blocks for this file, we should be able to determine what the maximum size of the file is, right? So how would I do that? And as a hint, this is really similar to figuring out how much memory we can actually access. If I just change block to page and pointer to PTE. So for disks, unlike virtual memory, the PTE stores essentially like a pointer plus a bunch of permissions. For files, it's just a pointer. There's nothing else baked into that later. We'll go into the next lecture where permissions and stuff would be. So if I want to calculate the maximum size of the file, how do I do this? Yeah?
Multiply them together and then multiply that by the block size.
Multiply what together?
The block size divided by pointer size.
Yeah, so I need to figure out first the number of pointers per block, right? So figure out the number of pointers I can fit on a block, and again, we can write powers of 2. So 8 kilobytes is 2 to the 13. 4 bytes is 2 to the 2. So this is just 2 to the 13 divided by 2 to the 2, which is the same as 2 to the 13 minus 2, or 2 to the 11. So I can store 2 to the 11 pointers on a block. Yeah?
I was wondering, just the previous thing about how the block, or the file size is limited by the max size of the block, can we not just use multiple contiguous blocks?
Multiple contiguous blocks?
It doesn't really matter if it's contiguous, but just multiple blocks, and then you just have infinitely big files.
So that would have to get into if I use multiple blocks for that, I would need to specify in the file how many blocks, and there's usually only a finite number that you have a finite number somewhere.
Right, of course, but it wouldn't be limited to just that many, right? If you could just use multiple.
So this is just assuming a single block, yeah. yeah, we're just single block right now. We can probably borrow an idea from virtual memory, like you said before, and have levels. But for now, this is like the same as one level. So that's how many pointers we can fit on a block. Each pointer points to a block. So the maximum size of the file, if I did this, would be 2 to the 11 times 2 to the 13. So that's the size of a block, which is 2 to the 24, which is, well, 2 to the 20 is a megabyte. So that's 2 to the 4 MIB. And you might notice I always do MIB. That just always means powers of 2. Megabyte is technically ambiguous, so that's why I write that. So 2 to the 4 is 16. So that would mean the maximum size of my file is 16 megabytes. Would you be happy if that was your file system? Probably not. That's barely a picture. So we can probably think of ways to improve this, stealing ideas from virtual memory. So I could have different levels, right? I could have a block of pointers that points to another block of pointers and follow that as many times as I want. And that's going to be what we solve and talk about in the next lecture. But it's basically virtual memory again, but slightly different and for files. But same idea, so good thing we learned that before. So we have some problem that, well, this is just that scenario that we just discussed. So maximum size, 16 megabytes, not good. So we started talking about file systems, how they enable persistence. So we described a little bit about how files are stored on disk. So far, the only thing that's actually used is that file allocation table, or FAT32. Usually, that indexed allocation, we're close, but we will talk about that in the next lecture as how to actually use that. And yes, spoiler alert, we will steal some ideas from virtual memory. But API-wise, you can open files, change the position. There's a position associated with all of them. And each process has its own local open file table, which is what a file descriptor is, pointing to a global entry that points to a file, has a position and some flags. And yes, we went over some allocation strategies for file. Again, the only one that's actually used is FAT, and we will get into the other ones later. So we can end early, 8 minutes.